Next, we have a short submission by Lewis Linson entitled Ionospheric Electrodynamics from Large Barium Releases.
My point, I'm just going to try and take a couple of minutes since I wasn't in the schedule, but my point tonight is try to point out that the observations of large barium releases in the ionosphere provide a means for determining some of the electrodynamic properties of the ionosphere. Small barium releases at high altitudes have been very useful to measure the electric field pattern on a worldwide basis now, carried out by Max Planck Institute and by NASA. And in terms of regarding the ionosphere as an electrical circuit, the small barium releases, which act as tracers, are equivalent to potentiometers. They don't disturb the circuit, they measure what's there. On the other hand, if you put a very large barium release in the ionosphere that significantly changes the conductivity, the gradients in conductivity will generate polarization charges that will change the ambient electric field. The resulting behavior of the large barium cloud, which can be observed, is influenced by the way the ionospheric magnetospheric system is reacting to these changes. Now on the first slide, first two I'm going to show two pictures of two different large barium releases, and then a third slide has data. Now I don't know if you're going to be able to see in these bright lights. Aha! It is there. Can you see it? I can't see it. You can't see it. Okay. Okay, let me go to my last slide. Whoops, you saw one there. These just don't show up, color slides don't show up in the light. But the point is, here is a cloud of neutral particles which is just blowing with a neutral wind, allows you to measure the neutral wind. Large barium releases allow you to make three measurements. One is the measurement of the ambient neutral wind. This is the barium ions. This part of the barium ion cloud is very low density and essentially acts as tracers and moves with the ambient E cross B velocity. This portion of the ion cloud is where the bulk of the ionization is for large releases. And this large cloud moves somewhere between this velocity and that velocity. And what fraction of these two velocities it moves is dependent on the conductivity of the cloud and, according to very simple models, the conductivity of the ambient ionosphere. The two barium releases I was showing were called Weather Vane 1 and Spruce, one near the equator and one at mid-latitude around L equals 1.9. They were at slightly different altitudes but of the same weight, payload. If one calculates the Peterson conductivity of each of those clouds, they correspond, and these numbers certainly in ratio are very good. This is essentially twice the conductivity of this one, around 35 mhos and 15 mhos, very significant enhancements of the ionospheric conductivities. The local Peterson conductivity is of order 1.5 mhos. By watching the motion of the cloud, one would deduce that the ambient ionosphere had to be something of order 10 mhos within a factor of 2. This ambient ionospheric conductivity is far too low. This particular release one could handle by bringing in the conjugate ionosphere, saying that there were field-aligned currents that were electrodynamically coupling this barium cloud with the conjugate ionosphere, which was in sunlight and therefore had a daytime conductivity, which would give a total integrated conductivity of order 7.5 mhos. So these simple models can be brought in agreement by deducing that there must be enhancements and depletions in the conjugate ionosphere. This cloud, on the other hand, near the equator, the ionosphere appears to be acting differently than the simple models. If one calculated the field line integrated Peterson conductivity, one gets very high values, even if you include the ambient, the conjugate ionosphere. However, the cloud did not move as though it were a highly conducting background. It behaved as though the ambient conductivity was very low, which must have some information in there about the dynamics of that region of the ionosphere. That's all.
Are there any comments or questions on?
The question was what determines a large release as opposed to a small release. Basically, by comparing the value of the integrated Peterson conductivity of the release compared to the ambient ionosphere. If the cloud conductivity is large, it will polarize and change the fields. If it's small, it won't change them and it will act as tracers.
Could you say whether the conjugate region for the spruce event was sunlit or whether it was in darkness? The conductivity might be different in that case.
It was in sunlight at the time. That was a January release from Florida at dusk. And the solar depression angle was about 17 degrees above the horizon, still in the conjugate region.
So you might expect, let me put it as a question, would you expect different results had the conjugate point been in darkness?
Yes, if that release had been done in June, I would have expected different results.